All right, thank you everyone. My name's Saul, and I'm going to present on egraphs in Python with a library called egglog. This is built off of a Rust library that I didn't write, but I wrote the Python bindings. So what are egraphs and what is this library? So the goal is to have a faithful binding to the Rust library, a Pythonic interface, and to have it be a base for other data science libraries to build upon when they're building expression systems or rewrite systems. So this library is really aimed at other data science libraries to use internally. So what is an egraph? Egraphs are like a data structure that comes out of the automated theorem proving kind of community and the equality saturation community, so basically from academic computer science, and they can be used to write rewrite systems, which can be used to write compilers. So another way to think about them as basically you define some types, you define some expressions, and then you write rewrite rules. They could be kind of like mathematical rewrite rules to convert between those expressions and then extract out like a lowest cost expression, and that would give you your like compiled form. So we'll go into an example because this is quite abstract. So we'll start by making a sort of a NumPy-alike array, right? An ND array, very simple here, just you can add or multiply and you can create an A range. So you notice that when I define this, I don't actually write bodies for any of these functions. All I'm doing is writing their signatures, their type signatures. And then I can write a rewrite rule. For example, I can say x plus x. I can rewrite that to x times 2, right? Those are like equivalent. And maybe x times 2 is faster for some reason. So one thing to notice, again, I'm writing this with just Python functions. I don't have to write any like, add class like you would if you were writing like maybe some other kind of system. And I can use, and this all works with MyPy and type annotations. So now I can make a function or an expression, a range of 10 plus 10. And if I add it to my egraph, it looks like this. So I'm adding a range of 10 to itself. So those are the two arrows here. The two arguments to add are the same expression. And then if I run my rewrite rule, I can see that this is now equivalent to the multiplication of a range with 2. So this here is the equivalence class, so it shows that these two expressions are actually equal to each other. You could substitute one for the other and you get the same result. And so then we can extract out our lowest cost expression for our input and say, okay, that's a range of 10 times 2. So this is a very tiny example. But I hope this gives you a flavor of what's working under the hood. And now I'm going to go with a slightly larger example. So let's say I'm using scikit-learn and I'm doing some kind of classification. And let's say I want it to go faster. So I might want to try to use numba, right? But let's say numba actually doesn't support scikit-learn, so I can't wrap a JIT decorator on this. It's not going to work. So what can I do? What I can do is I can use the egglog array API implementation and pass that into my function. And basically execute this scikit-learn function on an abstract array. So I make some assumptions about the shape and d-type of my input, but I don't know anything about the data. Skip that. And then what I get out at the end is this huge, long, abstract expression, which is what scikit-learn is actually doing under the hood when it's doing this function. So you're basically extracting out the information that scikit-learn is performing. And then we can actually compile this back to Python code. So you see now we just have a bunch of NumPy operations. We see we have the SVD, which takes most of the time here, but there's a bunch of other stuff that's going on. And so this is a form that actually numba can optimize, right? Numba can handle standard NumPy fine. This is also a graph representation, which is very small and really ineligible, but you can get a sense of like this is the form that scikit-learn is generating. So then we can call numba on it. We can do a little benchmark, and we can see, oh, wow, when I was doing my benchmark earlier, it was faster, and now it's slower. So there you go for a live demo. But it's at least equivalent functionality. So the conclusions here are not that you should use this instead of some other array optimizer, but that it's flexible enough to build systems like this that conform to the NumPy array spec. You could pass them in, and they work just like the NumPy array, but you can implement rewrites and add your own optimization. So hopefully it's a way for different array libraries or other data science libraries in the Python ecosystem to work better together because they can compose more easily. One library could just write the ND array interface, and another library could write rewrites on it. So there could be a greater, basically, collaboration between libraries. So thank you so much.
All right, nice job.